Again, I'd like to remind you, this course has a full part, as I mentioned in the first class. Before we really getting into the structure, reliability, we have to prepare what we need. So this probability theory I'm teaching you is really basics, okay? But that's what we really need to getting into the structure of reliability. That's what we are preparing. It's not only prepare, it's one part. When you're getting into structure reliability portion, you have to bring the model, probability model. So then you have to really know what kind of the models usually available. There are a lot of different probability models, but this course is not just for everybody, because it said reliability. Within the reliability is oriented to structure reliability. So it's more specific. So probability. Then I really want you to think about your area of research. So except Takashima, wait, you have any American name? Aline? Oh, that's good. My daughter's name is Irene. Aline. She happened to be the junior, so they don't really write the thesis or conduct the thesis research. But in your area, keep thinking about your work, thesis research work. Then some of you may connect it to the reliability problem, like a Jungan. Some of you may heavily even connected to that. Then a probability model you have to really develop into it from some experimental data or some available data, vice versa. So not today, maybe Friday, I'm going to introduce the probability model. The probability model we talked about was the Gaussian probability model. I call the probability the Gaussian probability density function, distribution function, or normal probability function. It's all same category, same family of function. So that's the most popular, and physics fit that the normal probability density function really well. Many physical phenomena fit in there, but not always that's true. That's why the next hour, not today. Today I have to introduce something else. At least Friday, I'm gonna do that. So then I'm gonna send out my short write-up, maybe 6-7 page write-up to summarize that model. But that's not all, of course. That's not all, because lots of different models, probability models, are available. So to get the probability of the failure or probability of the survivor or structural reliability, then you have to develop the model. So that's what I'm concerning about the continuing, starting from the small project, then getting into the larger project, I don't want to say, oh, this is important, that is important. In the learning process, you have to absorb and then just use it in your area. That's the whole idea. Otherwise, you don't need to take this course. You can just go math department and take the courses. They have a few different, the probability theory, mathematical theory. Then, after we getting into the develop the probability model, then we have to know the personality. You just can't just go out and date with anybody, right? You have to know the really important personality. Okay, whether it's gonna really fit, or would it be really nice to connect with the other person. So personality. All different probability model has a very unique personality. That's what, if you look at carefully, that's what I'm doing it. Like a mean, standard deviations, the variance, covariance, skewness, kurtosis, or median, or mode. It's all defining process of personality of the model. And that's what I connect. If you look at so far, we develop very simple personality. No skewness. If it's too much skewness, it's not very good, usually. But some physical phenomena, you can avoid the skewness. You can avoid the kurtosis. You can just set equal to 0. You can, because it's a personality. When I say personality, I'm talking about the characteristics of the physical phenomena. That's what we have to live with it. Okay? We have 24 hours a day. You can change it to 28 hours a day. You can, because there's a God's plan. That's a God's territory we can't control. So some physical phenomena, we have to live with it. Okay? So as you learn the change of the variable, we use a change of the variable technique to develop the probability function of the functions of some variable. Then that's a very straightforward approach, but that's a very useful, for example, approach. And could it be 1-to-1, could it be 2-to-1, could it be 10-to-1, the vice versa. Okay? And among the probability, like today's lecture, I'm going to start like conditional probability. It has a specific condition. It's a given. Condition means it's given. Okay? And in mathematics department, of course, when they teach the probability of the whole semester, then they go through the just more than definition. But conditional probability, I'm going to just start here, just for definition. I'm going to, I hate to say assign, rather than assign, as I see you all, in your office, you really study hard. Sometimes, not every week, sometimes I came in the evening. You are busy, sometimes I'm busy. I have to prepare presentation, not only here, outside, here, there. So I have to come back in the evening. Then I see all there, studying hard. So in your other time, you have a lot of time, but you have a lot of work to do. I want you to spend a little bit more time than just one additional hour for this course. So I'll just point out, okay? For example, conditional probability. What is the conditional? I'm going to really explain the definitions. And I would rather encourage you, as I already said, getting into internet. In my era, we didn't have internet. We have to go in the library and just search for it here, there. But here, conditional probability, you just type in keyword conditional probability, then you will see the tons of information. And if you just punch in conditional probability, I tried this morning what it shows up. And there is a conditional probability, just a list of all the area where you can find. And I want you to spend maybe 30 minutes or hour max after you type in conditional probability. Then it lists out quite a few, but look at the second kind of the address. I look at that address is www.mathgoodies, GOODIES.com. Very basics of the basics is what you need. I guarantee you do not need starting equation after equation. For research mode, I want you to start from the basics of basics and definitions to really understand the implication of such items first. If you go in there, then it has a pretty good few very fundamental example problem. And I want you to do that. It has about a dozen examples, very short question, really pushing around the basic definitions, okay? So that's what we're going to start that. And after you have a pretty good hand on such a probability model, what's the next step? Then you feel a little bit more on casting physics into the mathematical model called the probability model. Then you have to bring that model into your formulation of a structure reliability. So I'm going to start, when I start that portion, I'm going to use simple mechanics part, and some of it has that did not major, of course not majoring structure mechanics, but chemistry, that's okay. You have to spend a little bit more additional hour, like a strength and the load. A simple relation. You apply the load in the bar, simple bar, and it has a strength. Then it has all the information on the strength. For example, in terms of resistance. So it has yield stress, the linear elastic region, getting into nonlinear, then getting into ultimate strength and break into two pieces. it has, strength has a distribution, probability distribution, right? Who is missing today? One missing. Two. 중간 is missing. Who else? Jingyu is missing. Okay. When you are not able to come with some other incident, please send me an email or call me. That would be nice. Think this way. If I simply just don't come, does it generate a problem? Yes. If I simply don't come, then it's a problem. So, like 중간. Suddenly I don't recall your name. That's funny. Anyway, they told me last Friday I have this to attend. Would be very nice. What did I say? What did I say? Oh, strength. It has a probability model. Some very good quality bar may have very small, extremely small, the standard deviation. Then you can treat this bar as rigid. Then treat the strength as deterministic. What's the value, what's the probability model for that situation? That situation is straight up, right? No uncertainty in there. Then it's a deterministic, and probability model is simply the spike. Otherwise, it has could have a normal distributions, log normal distributions. Of course, I'm going to cover that log normal. That's very useful model. Then after that, the loading. So loading, actual loading in terms of kilogram force or in terms of the stress. Like L, people use L or S. Then now this is a probabilistic model for resistance, probabilistic model for load. Then now you are in the position to compute the probability of the survivor. Okay, that's what the beginning of structure reliability, simply beginning. Then eventually go down the formulation. You have to formulate before you solve. So of course, if you have up to 2 random variables, it's very easy to see it. Because the 2 random variable, when you are dealing with the probability density function, is simply the curve in the 3D space. Very nice. But if you have a 3 random variable, 4, 5, 10, then it's very difficult to visualize. So then you are in the position to solve the problem. Then we could say, well, we have optimization technique using the linear and nonlinear programming. Then now you have to, before you proceed, you have to learn the optimization technique. Well, some people could say, no, don't worry, we have a canned program, so you can just use that canned program. My answer is yes. However, you have to know the whole implication before you're getting into optimization. Otherwise, you can just fall into so-called the local minimum problem. So then you will just wondering where I am, which is not desirable. So So structure reliability formulation is rather straight if you really pay attention. Once you have a grip on it, then very comfortable. Then you can just march forward. That's what next step is. Then we're gonna generate, you mostly gonna generate the project problem to solve realistic problem using the structure optimization methodology. The reason I'm really spending some time this morning is some of you could really say, geez, why I have to redo or doing the basics of probability theory. That's the main reason, to develop into the probability model, then we can really prepare and use it for structure the reliability, okay? Otherwise, as I see you, some of, at least 80% took the course, mathematical probability theory. And in this course, I really want you to really use it in physics and engineering side of it, rather than just to let it happen in the mathematics. That's the whole idea, okay? Fair enough? And conditional probability, if you took the course in probability theory, then you maybe visit that area, have a good grip on the conditional probability. Conditional means is something given, right? Something is given. And as I indicated, conditional probability, just to punch in, then you can see the internet address, math goodies, then go in there. There are a few, about dozen problems. Please try to solve it, get the grip on it again, okay? Refresh your understanding. So it's a conditional probability. Implication is conditional. Conditional, not absolute. So usually we can write the conditional probability in the volume space. I'm going to say X, this is Y, this is Z, and usually this is joint. Did I cover the, I think I covered the basics of a joint probability density function. So it's like if I draw like a normal distribution type, of course you can draw the contour point in there, and I'm going to draw this is straight lines, okay, and this is straight line here on the XY plane, and this point I could say Y. Arlene, can you see Y here? Y plus delta Y. So this width is delta y. Then I'm going to just cut this volume, fxy. So if I do that, I'm going to put up like and I can draw. This is a slice, okay? This is a slice, so I can say shade. I'm going to shade it. And I'm going to just draw this shaded area. Okay. I have joint probability density function. Then I'm going to cut. That cut plane is normal to xy plane. Okay. And get the slice of delta y amount of the volume. So this is what this is. I think it's clear. You know, it's so funny. I just ask, then answer myself. Oh, clear, it's clear. Then here, I'm gonna say this is x point, this is y, this is x. I'm gonna put a little bit here. X. So here I'm gonna say this is x plus delta x. I'm going to cut at x and x plus delta x. So if you do that, I can see, then cut it this way. You can see that tall high. If I just rewrite like this. Can you see that the differential volume shown right in here? You know, cut it at x and x plus delta x. Then you can just cut the differential volume like this out of shaded area. And this is gonna be delta x. This is gonna be delta y. And this is gonna be fxy, xy. So conditional probability is nothing but the ratio of differential volume, this volume, over that sliced volume, given this volume. Always conditional probability is usually people use the p lowercase of the p, but doesn't make any difference. P x slice y. So this is really telling, this is a given. Conditional probability of x. Probability of x given y. So you can write this guy as conditional probability function for x given y. conditional probability, something given. In this case, is given is slice the volume. Slice the volume. Then you designate the differential volume. So if I just write the notation, it's like y, xy, dx is simply showing ratio. This is elementary volume over the volume of shaded strip. It may be a good idea to rewrite, even if I send out files which has all this. The reason is this is really 잔소리. It's a nuisance talk, but it's a good idea to see it, to write it, to talk. That's the best to remember. I'm not insisting to write, but elementary volume is this differential volume, which is f xy times dx dy, and this red strip volume is dy. Dy is the width of the strip in x direction, okay, times the whole area from minus infinity to infinity in x direction. Then you have to integrate to get area. So minus infinity to infinity fxy xy dx. So if you do that, if you really integrate out in the x direction, I can rewrite this guy as, which is a function of just the remaining parameters of y and dy. I'm sorry, not dy is already over here. So if I just rewrite this guy, fxy xy dx dy is equal to fy y times dy, which is equal to fxy. Now this is a conditional probability dx. So then dy cancels up. You can really set dx cancels up. Then conditional probability density function is x given, this means given, is equal to fy y, and top is fxy fxy. This is a final equation form for conditional probability. And the next step, what do you do? Then today is Wednesday after class in the afternoon, after lunch. You sit back, then going into math goodies, and don't spend more than an hour. It's not worth it. But it gives you really fundamental, really fun problem. Then you can just go through it, then has a good grip on the conditional probability. Then when the time arises, then you can use it with the correct concept, correct the definitions. And what happens if x and y are independent? When I say independent, what does it mean? Bachelor state, okay, has no connection between two random variables. It's really, really independent. Then independent, there is no conditional stuff at all. There is no conditional. I don't care what you do. I just do my own things. That's what the independent, statistically, of course, independent means. It said x given. Who cares about the given? And this is going to be simply say, this is, I simply ignore the action of the y. X is bachelor state. So if you do that back into here, so fxy, xy is equal to fx x times fy y. Whenever you solve the problem, one condition you would do is what happened for independent situation, random variable situation. Then you can really see that what's happening. I talked even this morning about the skewness, kurtosis, and other parameters like a mode, median, other parameter like a variance and mean we did already. Before I getting into skewness stuff, what is the mode means? What would be the mode? I'm going to say probability model. What's the mode? I didn't cover. Just talk louder. Ilyong, right? Ilyong? Yeah. Mode is the highest point. Then you are dealing with corresponding the x value. That's a mode, right? This is a mode. What about we can to remember your name. I know most of your name. So the next person's name to remember is Sungtae. Sungtae, what's the median? Median. There is a median. Another, before getting into kurtosis in equation forms, what's the median? Juil. 0? 0.45? 0, half you mean? Yeah. Yeah, that's correct, Sungtae. Half area. If you, this is the, let's say, point, that area is equal. What's the total area? Regardless, is 1, right? So median is the point, the probability density area is same. This area is same as that area. This is called, this point is called median. Clear? These are characteristics of the model. You can compute that, of course. How do you compute the, well, mode is easy, highest point. What about the median? How do you compute that? Area is 1. Median, this area up to here is half. Right? Half. So you can just compute, gradually increasing random variable. When it hit the 0.5, half, then that's the median. Now how do you get the skewness? What's good for it? Skewness and kurtosis. Skewness, as the name said, skewness is again personality check. Very important connection, analogy to human life. You are under 20, I'm sorry, not under 20. You are not under 25, no. You are between 25 and 30, correct? Even Higyu, you are over 25. No? You are not over 25 yet. Okay. So a person, this is really to study personality. It has a complete connection to the human life, so you can use as an analogy. That's what, when I taught such a long time, I said, wow, it's amazing. God created all the natures which you can really, through the nature, you can really predict what's happening to human life. Identical. Well, let's move on. Okay, skewness. Skewness is skewness of the probability model. Okay, like a normal density function. The behavior. This is one of the behavior of probability model. Then you have to really, by looking, okay, skewness. Skewness, the probability model could be like this, or probability model Could be like a normal distribution. Sometimes a probability model could be like this. By looking at the physical data, when you plot it, oh wow, this is what you have. Then you can tell right away it has such a skewness. In reality, then you are not going to pick up the Gaussian model. Why? Well, skewness is equal to 0 for Gaussian model, so you're not going to pick it up. Then surely you will pick it up something like extremal distribution, type 1, type 2, or type 3. Or you can pick up Rayleigh distribution, or chi-squared the probability model, because it can handle the skewness. This kind of the skew to the left is positive skewness. Okay? It's a positive. In such a normal distribution, skewness is 0, then of course no skewness. And this is a negative shift toward the positive, let's say, x direction, then that you call the negative skewness. Then question is, what's the skewness? Skewness is, I'm going to just simply say skewness, measure of the skewness is equal to x minus mu x cubed. Okay, it's a cube. E is expected value. So expected value, what's the definition? Expected value is simply x minus mu x cubed fx x dx. This is a cube. Whenever you subtract mu x, mean of x, it has a name in it. It has a name called central moment. It has a name in it. Central moment. So central moment, usually use notation C. Central moment. Let's say N central moment. What that means is when you're dealing with this kind of the expected value, this is N. Everything is a shifted amount of the mean value. The variance is a second order, the central moment, right? Expect the variance is N is equal to 2. So this means is equal to minus infinity to infinity x minus mu x n power fx x dx. If n is equal to what? We covered this before. When n is equal to what? What's the value? N is equal to 1. Louder. Standard deviation? 1령. Yes, sir. You can answer. When n is equal to 1, Well, let's start from n is equal to 0. What do you think? When n is equal to 0, what's the value? What's the central moment? Zero order central moment. Aline, smile. Good. This is Wednesday morning. What would be the value? Say 0. Why 0? When n is equal to 0, when n is equal to 0, which is x minus mu x, right? This is equal to e to the x minus e to the mu x. This is equal to mu x, right? Minus, this is a constant. If you take expected value of the constant, what's the value? Which is simply mu x is equal to 0. This guy is what? Integration of mu x fx dx, right? So mu x is out. Mu x integration fx dx minus infinity to infinity. This is equal to 1, right? Definition, right? 성태, right? Is 1. Answer is mu x. So this is equal to 0. Personality, central moment. When n is equal to 1, what is it? N is equal to 1. So which means e x minus mu x. Oh, wait a minute. I'm sorry. Sometimes teachers screw up, of course. Okay? I'm going to say, Yunsuk finally said, hey, you screwed up. Should say 1 minute early. So this is equal to 1. And this guy goes like this, is equal to 0. Then this is 0. This is equal to 1. Because this is a 1. So, sorry. And what happens when n is equal to 2? So e to the x minus mu x squared. This is called the variance, right? And now n is equal to 3, then e to the x minus mu x, third power. This is called the skewness. Third power. Then what happened? N is equal to fourth power, x minus mu x, fourth power, which is called the kurtosis. Okay? So here is the definition of the kurtosis, the skewness. And of course it has a unit on it. So to normalize it, this skewness, e to the x minus mu x cubed divided by sigma x cubed, normalized by sigma x cubed, then it's dimensionless, right? No units in there. So just a number. And this is what the number, if this is a positive, then it skew like that. If theta is 0, then like this. When theta is negative, then it goes like that. I'll stop here. I'll see you Friday.